Good morning to everyone. Myself, I am G. Charan from Triple E branch. Today's my tech talk topic on network analysis is performance study of a class E power amplifier with tuned series parallel response network. In this new topology of the load network is introduced in the class E power amplifier. The simple analysis and numeric results show that some improvements on output power, maximum utilizing frequency and device stress can be obtained by the new design method. Some simulations and experimental tests of this subclass are carried in contrast to the typical one. The design example uses an LDMOS transistor. The proposed amplifier's drain efficiency is 85.6% and output power is 33 dBm at 200 mHz. The results validate the feasibility and improvements of the proposed subclass. The switching device in a class E-tuned power amplifier can be a thyristor instead of a bipolar or MOS transistor. If the load network provides a switch current which nominally has zero value and zero slope at the time the switch turns off, the thyristor greatly enhances the power handling capability of class E amplifiers and is especially attractive in low frequency, high power, high efficiency applications. It is shown that the thyristor turn off time is substantially reduced by the class E amplifier operations, which keeps the thyristor at low junction temperature and provides low reappeal voltage rate to it. Laboratory results are given. Theoretically, predictions. Input power depends high efficiency power amplifier by employing a dual mode operation. Design approach. The proposed amplifier scheme provides two different operating modes depending on the power level, low or high input power modes. By controlling the number of operating amplifiers in each mode, the efficiency of the amplifier at low power level is substantially improved. Four single stage LDMOS power amplifiers with the Motorola MRF were incorporated with a dual mode input power divider and output power combiner. In the proposed operation, either one or four amplifiers were activated. The measurement result shows a 50 dBm saturated output power and 40% PAE in high input power mode. When four amplifiers are active by switching the operations to the low input mode, when the input power was relatively low at a 5% increase in PAE was obtained. Through his research, Sokolow demonstrated that this operating mode was capable of achieving nearly 100% efficiency. Later realized the benefits of the Sokolow's innovation and their expanded the work by using Fourier analysis. Investigation through a series of work in the end, Zolnitz defined an exhaustive set of equations that completely describe the class E frequency domain condition. 78.5% power added efficiency is the maximum attainable for class B. This class is often used in high power applications where efficiency is important. Class B. A typed device on one conducts currents for half of the conduction cycle as 1.3 power is only be dissipated when the device is on. Since power distributed in the transistor is voltage times currents, a net power saving is realized. In this amplification class, two devices be used for pseudo-linear amplification. This configuration resembles the push-pull output stages used in audio. Applications for class B operations, each transistor is derived 180 degrees out of phase through a necessary coupling transformer since there are no DC bis current. No power is dissipated when there is no input signal. In this amplification class, 180 degrees out of phase cross distonion can occur when the two amplification change. This reduce the overall linear of the configuration. Class E is a relatively recent Class E is a relatively recent amplifier format. In this instance, as in Class D, the device is operated as a switch. In either case, any parasitic capacitance is usually determinantal. Unlike Class D, through the parasite drain depletion region capacitance can be resonated with the inductive load when conferred. Because of this, class E can in practically achieve very high efficiency also. Contrary to class D, there are no short circuited current that results in efficiency losses. This design also requires careful selection of the typical shunt resonant circuit to reduce the high harmonic level. Voltage and current waveforms for this class. In this instance, the unique characteristic is that the drain voltage is driven well into the mode region. This key fact has significant positive effects on efficiency measures because the switch only turn on when the drain to source voltage is almost zero. There is a very little power dissipation in the device. Power dissipation in the device is simply drain to source voltage 1 tripled by the drain current. Therefore, when the drain voltage is reduced before drain current is drawn, efficiency increases. In fact, this form of application can ideally achieve 100% efficiency. A second order series resonance circuit consists of in series at resonance voltages across and are equal and opposite, and these voltages are many times greater than the applied voltage. They may present a dangerous shock hazard. A second order parallel resonance circuit consists of X and in parallel at resonance currents in and are circulating currents, and they are considerable larger than the input current. Unless proper consideration is given to the magnitude of these currents, they may become very large enough to destroy these circuit elements. Resonance is the phenomenon which finds its application in communication circuits. The ability of a radio or television receiver to select a particular frequency or a narrow band of frequencies transmitted by broadcasting stations or suppresses a band of fluence from other broadcasting stations is based on resonance. Thus, resonance is desired in tuned circuits, design of filter, signal processing, and control engineering, but it also to be avoided in other circuits. It is to be noted that in a series X circuit and the circuit acts as short circuit as resonance of if X minus X in parallel X circuit, the circuit acts as open circuit at the resonance. A parallel resonance circuit stores the circuit energy in the magnetic field of the inductor and the electric field of the capacitor. This energy is constantly being transferred back and forth between the inductor and the capacitor, which results in zero current and energy being drawn from the supply. A parallel resonance circuit's energy in the magnetic field of the inductor and the electric field of the capacitor, this energy is constantly being transferred back and forth between the inductor and the capacitor, which result is zero current and energy being drawn from the supply. Parallel resonance is a resonance condition that usually occurs in parallel resonance circuits where the voltage becomes a maximum for a given circuit. Being a parallel resonance means the impedance is high and inrush surge currently relatively low compared to a simple capacitor. Relatively low compared to a simple capacitor. Thank you.